So our first speaker for session 6 is Dr. Jennifer Barnes from KITP UC Santa Barbara. She'll be giving us an invited talk. And I'm very excited for this talk because she's the one we have to thank for correctly predicting the spectrum of a kilonova 4 years before we actually discovered it and saw it. So thank you, Jenny.
Oh, thanks so much, Mansi. Yeah, and thank you for the invitation to come here, and thanks for everyone for attending the talk. So I'm going to talk about multi-messenger astronomy with the Roman Space Telescope. So just to get everyone on the same page here, I think for our purposes for the next 25 minutes, we'll say that multi-messenger refers to gravitational waves plus electromagnetic radiation, but of course neutrinos can be another potential messenger. I'll be focusing on the GWEM side of things. So the current ground-based gravitational wave detectors that are operational, not right now, but in the general present, like LIGO and Virgo, are sensitive to kilohertz gravitational wave signals, which is pretty much exactly the frequency that is emitted by compact object mergers. So the mergers of neutron stars or black holes with other neutron stars or black holes. Of that set, the mergers that Roman is going to be interested in are those that include at least one neutron star. So we'll be talking about neutron star mergers or neutron star black hole mergers today. And as Mansi kind of indicated, I'm a theorist. So I know there are a lot of upcoming talks in this session that are going to get more into the technical aspects of getting these observations. And my goal here today is just to give kind of a theorist's overview of what we expect these events to look like, why they're interested and why they are so well matched to Roman's capabilities. So I will leave the more technical, observer-oriented discussion to the experts that will be speaking later in the session. Okay, so neutron star mergers or neutron star black hole mergers are really exciting in part because they have so much to tell us about so many different areas of astrophysics. So obviously such a merger is kind of the final stage in the life cycle of a massive star binary. So they have things to tell us about stellar binary evolution. Of course, they touch on general relativity and dynamics in the strong gravity regime. They also, although I won't be getting too much into this today, could reveal a lot about the production and the evolution of astrophysical jets. The neutron star merger and what happens in the merger aftermath is mediated by the neutron star equation of state. So from multi-messenger observations, we can learn a lot about the architecture of kind of some of the densest, the densest things, I guess, that we know about in the universe. And finally, as I will talk a lot about, they could help reveal the origin of the heavy elements. So let's start by reviewing what happens during these mergers. This is just kind of a little cartoon picture, but you can imagine that it's a nice animation with like beautiful, a beautiful artist rendition with dramatic music and stuff like that. So of course, crucially, the final few orbits of such a merger are going to emit a really luminous burst of gravitational waves. This is what's detected by the gravitational wave detector network. And this is kind of our heads up that an electromagnetic signal is going to be following shortly. And then we have the coalescence and the merger itself. So any neutron star in the system is going to be partially disrupted in this process. But actually, most of the mass is going to go towards forming a central remnant, which could be either a neutron star or a black hole, or perhaps a neutron star that eventually collapses into a black hole. But let's focus on the disrupted material for now. So some is going to be immediately gravitationally unbound, and that's just going to be kind of flung out towards infinity and fly away from the system. But some is going to remain bound in an accretion disk, and although matter can later be unbound from this disk, so we have separate potential stages of mass ejection here. But at the end of the merger, what we're left with is a central neutron star or black hole that's surrounded by an accretion torus. And then outside of that, we have this additional unbound ejecta just coasting away. Accretion onto the central remnant should power a gamma ray burst. So that's one potential electromagnetic signal. And this unbound material, whether it's unbound at the initial coalescence or later escapes from the accretion disk, we think will undergo rapid neutron capture, or R process, nucleosynthesis. So the R process is the nucleosynthesis channel responsible for producing about half of all elements heavier than iron in the periodic table. And to do this, it has to capture many free neutrons onto seed nuclei in quick succession. So this is one of the reasons that neutron stars are, kind of such a natural fit for the R process, because they are neutron star material is of course very neutron rich. When you rip it apart, you easily make a lot of free neutrons. That said, the astrophysical site of the R process is still a topic of a lot of debate. And so kind of answering this question, or at least constraining this question better, is one of the things that makes multi-messenger astronomy so exciting. Anyways, so in order for the R process to happen, as I mentioned, you have to have a lot of free neutrons around to power these very rapid successive neutron captures. And it's really only once that supply of free neutrons has dwindled down that the nuclei, which by this point have undergone a lot of captures and are now going to be very heavy and neutron rich, have a real chance to beta decay back down to stability. So that's the conversion of a neutron into a proton, the emission of an electron and a neutrino, and then that kind of moves the nuclei into a more stable configuration, and eventually they reach stability. However, having passed through this early, very neutron-rich configuration ends up leaving you with a different final abundance pattern than the pattern that you would get if the neutron capture and the beta decay timescales were more comparable. So that's why you get a unique set of elements for these purple elements versus the green elements, which are produced in slow neutron capture, when the capture and decay timescales are a little bit more comparable. So I always like to give a more detailed look at the R process, just to really impress upon people how complex it is. So let's take a look at this now. This is an animation from a simulation of the R process that was carried out with the code Skynet. And there's a lot going on here. So the evolution of the gas is shown in the upper left, and the R process is explosive. So we have an expanding, generally cooling gas. The composition as a function of mass number is here in the opposite corner. So you'll see that evolve once the simulation starts. And then running along this diagonal is the chart of the nuclides. Stable nuclei are indicated with these black outlined pixels, and other pixels are color-coded according to abundance. So right at the moment when the R process is starting, we have this constellation of lighter seed nuclei. And then we have a lot of the mass tied up in free neutrons, which of course are all condensed into this one single pixel here in the very lower left. Okay, so then if we start neutron capture, you can see the initial phase is just one of building up heavier and heavier nuclei. So the composition is sticking to the neutron-rich region of the chart of the nuclides. It's growing heavier, it's growing more neutron-rich, and there we go. That was the point at which the free neutrons dried up. And now you see what's driving the compositional evolution is beta decay instead of this neutron capture. So, you can wait. Some of these nuclei have pretty long half-lives. So, if we wait, eventually everything will settle back down into stability, but it can take a while. The key point here, though, is that you have this nucleosynthesis process that's followed by this long decay phase happening in the debris that's unbound during and shortly after the merger. And the energy from these decays is going to provide a source of heat to that debris cloud, which is going to power, our kilonova. So one note that we'll come back to a little later is that kilonovae can come in slightly different flavors, depending on the exact mechanism that was responsible for unbinding the outflowing mass. So just something to keep in mind. All right, so it would be remiss to talk about multi-messenger astronomy without talking about GW 170817, which was the first neutron star merger that was detected in both electromagnetic and gravitational wave radiation. And that was back in the summer of 2017. So the earliest signals from these events were gravitational waves. The time frequency spectrum is shown right here. There's the characteristic chirp. So gravitational waves and gamma rays. But within 10 hours, astronomers that were searching LIGO's localization region had detected a kilonova counterpart in a very nearby galaxy that was only about 40 megaparsecs away. And then once detected, the counterpart was followed extensively in multiple bands. So each of these lines here represents a distinct observation. And for readability, I've omitted the X-ray and UV observations. So there was just a ton of data coming out of this event. It is all compiled here in this, very lovely plot, along with some, I think, analytic fits to the data to guide the eye. But this is the general picture we should have of the kilonova from GW 170817. And we learned a lot just from this one single event, of course. For one thing, it confirmed neutron star mergers as progenitors of short gamma ray bursts, which is something that had been theoretically expected for a long time, but was difficult to prove without this gravitational wave or without this coincident gravitational wave signal. It also identified neutron star mergers as sites of the R process nucleosynthesis, right? This, the emission that we saw, in particular, the red color of the emission, was pretty consistent with expectations of R process compositions. And it's also a pretty unique fingerprint. So it looks like this event did produce some R process. That said, we still don't have the whole story of, what kilonovae look like, what kinds of R process they undergo, what abundance patterns are burned in these events. And to see why, I think it's helpful to zoom out a little bit and look at the full landscape of binary neutron star and neutron star black hole mergers, and just, kind of how the different paths we think these systems could take as they undergo in spiral and merger. So to start with, obviously, things are going to depend on your initial conditions. So what kind of binary you have and the masses of the component stars. And then these kind of initial conditions, as well as the neutron star equation of state, is going to kind of mediate the in spiral and the mass ejection during the merger. It's also going to determine the fate of the central remnant, whether you have something that is, an immediate black hole or a long-lived neutron star, or maybe something in between, a neutron star that survives a little bit as a hyper supermassive neutron star and then eventually collapses as it slows down and rotation is no longer able to support it against the inward pull of gravity. So both these things, the mode of mass ejection as well as the fate of the central remnant, are going to influence exactly how the R process synthesizes elements. So I want to be clear that we're pretty confident that in any kind of mass ejection mode you would expect to get out of a compact object merger like this, we think that the R process will happen. The complicating factor is that the R process can produce a range of final abundance patterns. So these are the results of more R process nuclear network calculations from Skynet. But in this case, we're just looking at the final abundance pattern and showing how it depends on initial electron fractions. So electron fraction is just the number of protons per baryon. Counterintuitively, the lower YE, or the electron fraction, is, the more free neutrons the system has on hand. And it's only for fairly low YE that there are enough free neutrons in the beginning to build up, the heaviest elements, right? Free neutrons are our building blocks here. The more we have per seed nucleus, so when the R process turns on, the easier it is to manufacture heavy elements. Of course, neutron star material is initially going to be at a pretty low electron fraction, but we expect weak interactions to operate in certain post-merger environments, and these can turn neutrons into protons. So that's going to drive YE up. And if it does so successfully enough, it can change the outcome of the R process. So I've been talking a lot about these different modes of mass ejection. And the reason I keep circling back to that is that different kinds of outflows have different levels of exposure to weak interactions. And so we might expect them to have different abundance patterns. And as I'll talk about, that would lead to different patterns of emission as well. But I think the take-home point is that if we really want to, kind of untangle all of these dependencies, understand, what is going on in individual mergers, as well as understand the role of mergers as a population in our production on kind of cosmic scales, then what we want is detailed observations of what we expect to be a pretty diverse population of kilinovae. So it's certainly not set in stone that the kilonova we saw accompanying GW 170817, is the standard for this population. But one advantage we have when we're thinking about, what the diversity of kilinovae should be, what the potential world of expected signals is a fairly good understanding of how different kinds of R-process nucleosynthesis or different final abundance patterns are going to influence the emission that we see. So probably review for anyone in the multi-messenger community, but I'll go through it briefly just to be thorough. So the most important source of opacity for kilinovae, just like for supernovae or a lot of other transients, is bound opacity. So the absorption without ionization of a photon by an atom or ion. And the bound opacities of R-process compositions generally are either high or very, very high, depending on exactly the abundance pattern burned. Certain R-process elements like cerium, which is plotted in green here, or neodymium, which is shown in red, are very opaque to optical photons. So any kilonova with a composition that has non-negligible amounts of these kinds of high opacity elements will itself have a very high opacity. And as a result, it's going to shine at much redder wavelengths than, for example, supernovae. The main contributor to supernova opacity is iron, and you can see here that its orders of magnitude, or its opacity is orders of magnitude lower than that of some of these high opacity R-process elements over a really wide range in space. So I think that's just kind of a useful benchmark for thinking about how red these transients could be. The reason for the high opacity is the atomic structure of certain R-process elements. So atoms or ions that have a larger valence electron shell, have more ways to arrange valence electrons within that shell. And then since we know the periodic table is organized according to valence shell structure, what this means is that there are kind of characteristic opacities for different blocks on the periodic table. Right, but if you have a larger shell and more distinct arrangements, that means you have more distinct energy levels, since each arrangement is at a slightly different energy. This means that there are also going to be more transitions between energy levels, and each transition is a different photon energy that can be absorbed. So that means more opportunities to absorb photons, so a higher opacity. Elements with the largest valence electron shell are found in this block here. They're the lanthanides and actinides. So they are going to have the highest opacity, but these are also fairly heavy elements. So they can only be synthesized under very neutron-rich conditions. Otherwise, there just aren't enough free neutrons to build up to these very heavy species. So while we think that all mergers are going to make more high opacity atoms than supernovae would, for example, only outflows with the right initial conditions are going to make these very heavy, very opaque nuclei, or I guess atoms. That's not the nuclei that are doing the absorbing. Anyway, again, since initial conditions, or since the initial YE, it depends a lot on how the mass was ejected and what was happening in the aftermath of the merger. This relationship between composition and color is kind of a through line that connects, the details of the merger that are very hard to see directly with the nature of the emission that we can actually measure. So we can go back and apply this insight to the 170817 kilonova and take a look at its spectral evolution. Right at pretty early times, which shown on the plot on the left, you see emission that is peaking at blue and optical wavelengths. So this signals a low opacity and a weaker R-process that did not produce a lot of these high opacity lanthanides and actinides. However, over the course of the first few days post-merger, what we saw was the emission shifting to much redder wavelengths. So the emission started to look a lot more like, what we would expect for a kilonova that synthesized pretty large quantities of lanthanides and actinides. So, I think this is just a good demonstration of how complex kilonova emission can be. These are systems that we generically expect, or that we expect generically, to produce multiple outflows, potentially with their own patterns of emission. Okay, and in the final couple of minutes, I'll just pivot a little bit and actually, talk about the Roman Space Telescope, because I think, 1708-17 also confirmed the very red color of kilonova emission, which is one of the things that make Roman such an exciting tool for studying these transients. Okay, so the major advantage that Roman has for kilonovae is just its incredible sensitivity out to very red wavelengths, and that makes it really useful for kilonova discovery. So this is a nice plot that is comparing limiting magnitudes as a function of wavelength for Roman versus several other wide field instruments. Yeah, and you can see that, this is a telescope relative to its peers that's, well, I don't even think it's right to say its peers. This is a telescope that's in a league of its own, right? It doesn't really have peers. And it's especially sensitive at the very red wavelengths where the kilonova was shining, which I've indicated with this orange bar over here. So this led, some people who have done simulations of the Roman survey based on certain assumptions about, what the distribution of kilonovae will be, to estimate that Roman could detect around 16 kilonovae over 2 years, even without any gravitational wave triggers. So, if you think that we have really gotten a good look at 1 kilonova ever, the possibility of finding 16 in 2 years, kind of by accident, is pretty exciting. That said, Roman could absolutely be a powerful tool for gravitational wave follow-up. I say could be because, as far as I'm aware, there's not a formal plan to use it to follow gravitational wave triggers. But if that's wrong, I hope someone will let me know. Right, and that's just because it combines, this depth in the redder bands that we've already talked about with a very wide field of view that would allow it to efficiently search large gravitational wave sky localizations. So one of the challenges of EM follow-up, and one of the reasons that it took hours to localize a gravitational wave counterpart in the case of 1708-17, is that, we don't really have like a pinpoint on the sky. The error regions tend to be pretty large from the gravitational wave signals, and so it just takes a long time to sort through all of the galaxies in a given region, rule out false positives. So something that can, see deeply in red bands and efficiently search potentially large volumes could be really, really useful. I think as time goes on and gravitational wave detector networks become even more sensitive and are able to see farther, or are able to see mergers that are located farther and farther out, Roman's advantage just kind of increases because it's going to have a much better chance of seeing kind of these threshold events that will be faint and redshifted. So in fact, in the same paper that estimated that Roman could see 16 kilonovae in survey mode, it was also estimated that they could potentially detect kilonovae out to a redshift of 0.8. So, as gravitational wave detectors improve and we start to get a real sense of how, yes, we could get a much better sense of how mergers are distributed through space and through redshift, and get a much better picture of just how these merging systems are assembled, and think about things like evolution with redshift. All right, so the final thing I want to know is that, I've kind of implicitly been talking about photometric detection here, but a lot of information for kilonovae is going to be buried in the spectra. So I think, we can think about Roman as a tool for discovery. It could also potentially be a great tool for spectroscopic follow-up once a counterpart has been localized. So I think with that, I'm going to end the talk here. And as I said, I think we'll get into some more of the, observing strategy details with the talks that are coming up. But I am happy to take any questions that are, happy to take any questions that have come up over this talk. So thank you so much.
Thank you, Jenny. That it was lovely to hear how fundamentally read these things are and the relevance to Roman. I don't see any questions yet in Slack or in Zoom, but maybe Skylar, you can correct me.
No, I'm not seeing anything then.
So this should go into the session 6 Slack channel.
Yeah, and the Barnes thread.
So while we are waiting for questions, let me ask one, which is on the spectroscopy, the last point that you were making. What would you hope to see with the spectrum of Roman? So suppose Roman is following up a kilonova and gets this beautiful near-infrared spectrum. What would you hope to see? What lines would you be excited about?
Yeah, well, I think it's hard to pinpoint specific lines. So right now, the most confident detection of a single line that has been made is strontium, which is one of these lighter R process elements. The challenge with trying to identify particular lines in a spectrum is one, these R process compositions encompass many atoms. So you have a lot of lines that are potentially contributing features. And then you also have a really high expansion velocity. So things are going to be kind of, broadened and smeared together, and picking out individual features is going to be pretty hard. But I think the first step is just to try to accumulate measurements of the spectra, so we can start to look for patterns, try to find things that look to be like true features that are robustly present in kilonovae, and just kind of analyze for several spectra instead of just being limited to one, what features are turning up over and over again. But I think really the questions that people have are, how do you demonstrate that kilonovae, or that a given neutron star merger actually made some of the heavy R process elements? So we can make those arguments based on opacity, but it would be amazing to have the identification of a line, for something very heavy. So for like one of these lanthanides and actinides, or even for platinum or gold, which is something, you heard a lot of people saying like, oh, we know that neutron star mergers made gold now, but you don't see like a gold line in the spectrum. So yeah, I think the interest is in probably finding lines of the most massive elements we can, and then using that to try to really constrain what kind of nucleosynthesis happened in a given event.
Thank you, Jenny.